Hi, this is Sesh. Welcome to another lesson in data structures and algorithms. In two previous lessons, I described the different kinds of graphs and how to store graphs in programs. As far as the data structure of a graph goes, the storage is pretty much it. The specific operations that are used on the graph structure depend on the algorithms that are applied on graphs, of which there is a large variety in real-world applications. One such application is to find the shortest path between any 2 points, or vertices, in a directed graph with edge weights. In this lesson, I'm going to describe the widely used Dijkstra's shortest path algorithm, named after its inventor, Edsger Dijkstra. The algorithm works on any directed graph that has positive weights on its edges. Let's start by defining the problem and its solution on an example, then see how Dijkstra's algorithm arrives at the solution. Here's a directed graph with edge weights. We want to find the shortest path from point A to point F. In other words, A is the source and F the destination. There are several paths from A to F. There's ABDF, there's ABEDF, and there's ABEGF. Now let's look at the lengths of each of these paths. The ABDF path has a total length of 17, obtained by adding the weights of the edges A to B, B to D, and D to F. The length of the ABEDF path is 16, and that of the ABEGF path is 12. So the shortest path is ABEGF. Of course, enumerating all possible paths from source to destination, then picking the shortest of those, is a brute force approach that will quickly become impractical as the graph gets bigger. This is where Dijkstra comes to the rescue. He proposed an algorithm that works by trial and error. Start at the source and work through the graph by increments. In each increment, estimate the next best step to take, but if the estimate is off, then it is corrected in a future step. This is a so-called greedy approach because it goes for instant gratification, then repairs the damage, if any, later. And surprisingly, against all intuition, this algorithm works correctly and is much faster than the brute force approach. Okay, let's get into it. Imagine that you're starting at the source vertex A, about to embark on a journey that will eventually get you to F along the shortest path. At the heart of the algorithm is the notion of the current distance from the source for every vertex in the graph. The distance of A from itself is 0. You can get to B with one hop, traveling a distance of 5. Or you can reach C in one hop, traveling a distance of 10. The other vertices are not reachable from A in a single hop. In other words, they are not neighbors of A, and because you can only see the neighbors, the other distances may as well be infinity. In addition to keeping the current distance of a vertex from the source, we will also keep the previous vertex from which we got to this vertex. We got to B from A, so we record A as B's previous vertex. And we do the same for C. This will help us flesh out the sequence of edges in the shortest path when we hit the destination. This initial step sets up what's called a fringe containing B and C, both reachable from A with one hop. Next, you pick the vertex from the fringe that has the minimum distance. This is the vertex B. You remove B from the fringe and go from A to B. Now here's the neat thing. Dijkstra's algorithm says that when a vertex is taken out of the fringe, the shortest path to it has been found. Here, you've found the shortest path to B, which is the edge A to B. And if the objective from the get-go had been to find the shortest path from A to B, then you're all done. Now you might be thinking, what if the graph were different, and there was another path that wound through other vertices and eventually landed at B with an even shorter distance? The magic of Dijkstra's approach is that this is guaranteed not to happen, meaning that when you remove a vertex from the fringe, you are guaranteed to have found the shortest path to it, and you will not in the future find an even shorter path. This is why Dijkstra's greedy algorithm is practical. You don't need to look at all paths from A to B. Okay, let's carry on. We removed B from the fringe and went from A to B. From there, we can get to D and E. The weight of the edge BD is 6, and the distance to B from the source is 5. So adding these, we get 11, the distance of D from A. We replace the infinity with this new distance because it is less. And we record the fact that B is the previous vertex to D. Similarly, the distance of E is computed as 8, and its previous vertex is set to B. Since D and E have now been found to be reachable from A, they're both added to the fringe. As we repeat the steps of the algorithm, it would be helpful to track progress in a table, as shown here after the initial or zeroth step, and the first step that we just completed. The third through last columns show the current shortest distance of each vertex from A. B and C are in the fringe after the initial step. In the first iteration, or step 1, B is picked from the fringe and gets done, meaning the shortest path to B from A has been found. The B column effectively goes out of consideration, since B's distance will not change after this point. The distances of D and E are lowered to 11 and 8 respectively, and the fringe now contains C, D, and E. On to the next iteration. Of the vertices in the fringe, E has the lowest distance, so it is removed and is done. Going to E, its neighbors are D, G, and C. Let's look at each in turn. The new distance of D via E is 8 plus 2, which is 10. This is less than the current distance 11, meaning that the path ABED is shorter than the path ABD. So the distance of D is changed to 10, and its previous vertex is changed to E. Looking at G, its new distance is 8 plus 2, also 10, so its distance is reduced from infinity to 10. In other words, it is now seen to be reachable from A. The previous vertex of G is set to E, and it is added to the fringe. As for the neighbor C, the new distance via E is 8 plus 2, which is 10. This is the same as C's current distance, which means whether we go directly from A to C or A to B to E to C, it's the same distance. So there is no point in changing the distance of C. Let's update the table to reflect these changes. In the third step, we find that all the fringe vertices C, D, and G have the same distance. When more than one vertex in the fringe has the least distance, Dijkstra's algorithm says you can pick any of them arbitrarily, and you will still find the shortest path to the destination. If you were to pick one instead of the other, you may find a different shortest path. There could be more than one shortest path in the graph. So here, let's pick C and remove it from the fringe. Going to C, we find that it does not have any neighbors, so there is nothing more to be done in this iteration. The table is updated to complete the step. Now we're left with D and G, both with distance 10. Say we pick D and remove it from the fringe. Going to D, we find a lone neighbor F. The distance of F can be reduced from infinity to 10 plus 6, which is 16. So we update its distance, set its previous vertex to D, and add it to the fringe. And here are the updates to the table. Next iteration. Of F and G in the fringe, G has a smaller distance of 10, so it's picked next and removed from the fringe. Going to G, we see a single neighbor F, whose distance can be reduced to 12 if we get at it via G. So we go ahead and do it, and set F's previous vertex to G. And let's not forget to update the table. Now this is the last step. There is only one vertex F in the fringe. It's removed, at which point we have found the shortest path to the destination. And here's the completed table. The distance of the shortest path to F is at our fingertips. But what of the sequence of edges that make up this path? This is also available, but we need to trace it using the trail of previous vertices we have created, going backward from F. We can do this using a stack. Start by pushing F onto the stack. Then go to its previous vertex G. Push that on the stack. Continuing in this manner, we trace the chain of previous vertices. G leads to E, which leads to B, which leads to A. at which point we stop because A is the source. Now all we need is to pop the vertices from the stack, and out comes the shortest path. And that's it. But the story is not fully told yet. There's one interesting twist, and that is Dijkstra's algorithm runs until all vertices are done and the fringe is empty, even if the destination vertex was already encountered. In our example, the destination could have been any vertex, and the algorithm would still have run until the last vertex in the fringe f was removed. There's a reason for this apparent overkill. Remember that as soon as a vertex is removed from the fringe, the shortest path to it has been found. We can save this information for every vertex. Then, anytime we need to get the shortest distance to any vertex starting at the same source, such as A, we can simply look up the stored results, which would be much faster than running the algorithm over again. This makes Dijkstra's algorithm what's called a single source algorithm. If the source changes, we run it again and save all the shortest paths. Okay, to wrap it all up, here's the algorithm. S is the source vertex. In our example, that would be A. In the initial step, for each neighbor of the source, we'll set its distance to the weight of the edge from the source to it. So B's distance would be 5, C's would be 10. For all the other vertices that are not reachable from A yet, the distances will be set to infinity. And then we start up the loop and keep spinning it until the fringe becomes empty. In every iteration, we're going to remove the minimum distance vertex from the fringe. And when we do that, we know its shortest distance has been found. And that would be B in this case in the very first iteration. And then for each neighbor of this vertex we just picked, if the distance of the neighbor is infinity, then we would set its distance to the distance of the minimum vertex plus the weight of the edge from that to the neighbor. So for example, for D, it would be 5, which is B's distance, plus 6, so 11. And for E, it would be 5 plus 3, 8. And these two vertices would be added to the fringe. And otherwise, if the vertex is already in the fringe, so for example, if you think of the next iteration in which we pick E as the minimum distance vertex, we would look at its neighbor D and find that D is already in the fringe, in which case we'll be in the otherwise step of the algorithm. And the distance of D would be set to the current distance, which is 11, or a new distance, which is E's distance plus 2, which is 10, whichever is the lesser of the two. So obviously the distance from E is 10 less than 11. So D's distance will be replaced, and we just keep doing this until all the vertices in the fringe are removed. All right, that's about all of it. Hope you enjoyed the algorithm, and I will see you later.